You know that feeling when you find something that seems absolutely perfect, the winning ticket, the best possible result, only to find out later it was, well, kind of too good to be true? We're about to dig into this really cool paradox that explains exactly why the best answer can sometimes be a complete lie. Okay, so it all kicks off with something you might have actually felt before. Picture this. You win an auction, you got the thing, but then like 2 seconds later, you get this sinking feeling in your stomach. Did I did I just pay way too much for that? Trust me, if that's you, you are definitely not alone. Yeah, that feeling actually has a name, and getting a handle on it is the key, really, to spotting some seriously flawed logic. And not just in auctions. We're talking everywhere, from scientific studies all the way to how artificial intelligence works. So this whole thing was first really noticed in what are called common value auctions. This is where everyone is bidding on the exact same thing, like, say, an oil field. Now think about this for a second. Even if every single bidder is an absolute expert, who's going to win? Well, it's almost always the person who was the most optimistic, or, let's be blunt, the person who overestimated what it was worth the most. And that is the winner's curse. Just by the simple act of picking the winner out of a whole bunch of different estimates, you're pretty much guaranteeing you're picking an outlier, one that's way up on the high end. In a way, you're literally selecting for the biggest error. Now, what's so wild about this is how the winner's curse just pops up in places that look nothing like an auction. Let me show you a fantastic example of what I mean. All right, just imagine a group of scientists trying to find a link between jelly beans and acne. So they test the purple ones, nothing. The brown ones, nope. Pink beans, still nothing. Test after test after test, they just keep coming up empty. So they run, let's say, 20 different tests. 19 of them show absolutely no link at all. But then, the 20th test, the one on green jelly beans, bam, it comes back positive. They're like, whoa, we found it. We actually found it. And this just perfectly shows the problem, right? The news goes crazy reporting this one positive finding. But think about it. Because they've cherry-picked these single winning results from a massive pile of tests, it's super likely that it's just a random fluke. We've fallen right into the trap. We've cursed ourselves by only paying attention to the winner. Okay, so this isn't just, a weird coincidence or some kind of bad luck. Nope. This is actually a fundamental, baked-in feature of how math itself works. It all comes down to a mathematical rule called Jensen's inequality. Now, don't worry, we're not going to get bogged down in the scary-looking formula. The main idea is actually pretty simple. For any kind of bowl-shaped function, the high points have a way bigger impact than the low points. So what that means is the average of all the results you get from the function is always going to be higher than the result you'd get if you just plugged the average input into the function. It's a subtle but really important difference. And here's the kicker. The function for finding the maximum, the simple act of just picking the biggest number out of a group, it behaves exactly like one of those bowl-shaped curves. Why? Because it's super sensitive to the highest value, and it completely ignores everything else. And that brings us to a really powerful conclusion. If you take a whole bunch of estimates, even if they're all perfectly unbiased on average, the maximum of those estimates is always going to be biased high. Just by picking the best one, you've pretty much guaranteed you're overshooting the true value. Now, this isn't just some abstract problem for math nerds, okay? This is a huge, everyday challenge in the world of machine learning. See, when we train an AI model, we're not just running one simple test. We are, for all intents and purposes, running millions and millions of tiny little experiments, all at once. The whole time, it's searching for the single best way to explain the data. The algorithm is constantly picking a winner. It's looking for the best internal settings, or what we call hyperparameters. It's looking for the most powerful combination of features. It's trying to find the best type of model out of a gigantic list of options. It's like we're running that jelly bean experiment, but on a planetary scale. And if you're not super careful, this whole process can create this powerful illusion, this mirage of a model that looks absolutely perfect on the surface, but underneath, it's totally flawed. Take a look at this, for example. This comes from an algorithm called one nearest neighbor. Now, this thing is so flexible that it can literally draw a perfect, custom-made border around every single data point it was trained on. So if you judge it on that specific data, it looks like an absolute genius. I mean, it gets 100% accuracy. Perfect score. But here's the thing. Testing a model on the exact same data it learned from, that is a classic trap.
It's called the resubstitution estimate. And yeah, it looks super impressive, but it tells you absolutely nothing about how that model is going to do out in the real world.
And why is that? Well, it's the winner's curse just cranked up to its most extreme level. The algorithm has sifted through a practically infinite number of possible explanations just to find the one that perfectly fits the data it saw. Of course it looks good. It was literally chosen for that one specific job. So how do we get out of this mess? How do we escape the curse and get a real honest-to-goodness measure of how well a model performs? Well, thankfully, the solution that data scientists came up with is actually incredibly simple and elegant.
It's called the holdout method, and it's brilliant. First, you take all your data, and you just randomly split it into two piles. Then, you let the algorithm go to town on the first pile, the training set. You let it do its whole thing, search through every possibility, run all its little experiments, and pick its absolute favorite #1 winning model.
But then, and this is the absolute key, you take that winning model and you test it on the second pile of data, the one you held out, the test set. And because this data had nothing, and I mean nothing, to do with picking that model, the curse is completely broken. The score you get from this test, that's your true, honest, unbiased estimate of how well it's going to perform in the real world. So the big takeaway here is this. From now on, whenever you see a result that's being celebrated because it's the best or the most significant one out of a whole bunch of tries, be a little skeptical. Now that you know all about the winner's curse, you have to wonder, what other winning headlines, what other miracle products or supposedly perfect results out there are actually just statistical illusions?